Um, we'll have Aram Harrow tell us about an approximate super selection principle for entanglement.
Great, thanks for having me. Sorry, I couldn't be there in person. This actually, so this is of course the reunion workshop for the original workshop that I wasn't at. But I'm going to tell you about a line of work that's basically started with my earliest paper, like the beginning of my career was thinking about these topics, and which got a big boost from a previous Simons reunion workshop where I gave a talk about something and Mario Zegedi gave a talk about something, and then Dorit Aharonov stood up and said, aren't you two talks basically the same thing? And we merged and had this fun paper. Yeah, so I'll tell you about a range of things, many of which I'm thankful to my time at the Simons Institute for advancing. And the story begins by thinking about the resource picture of bipartite pure state entanglement. The usual story is Alice and Bob share some pure entangled state, and the space of all possible pure entangled states is maybe quite large, but you can simplify the picture with local unitaries. And if you assume that these are free, they can transform into this Schmidt normal form, and the conserved quantities are these lambda I, the Schmidt coefficients. Of course, there's still many of these. So with LOCC, you can further simplify things. You get this partial ordering based on the majorization relation. You can convert lambda to mu if lambda is majorized by mu, if mu is more concentrated than lambda, that means it's less entangled. This too, of course, has many inequivalent forms of entanglement. So things really simplify when you get into the asymptotic regime. So if you have n copies of a state, you can approximately interconvert it to n EPR pairs, where E is the entropy of entanglement. So this approximate interconversion was an enormously successful idea that I would say launched the entire idea of resource theories more generally in quantum information theory. This is now a 25-year-old paper due to Bennett, Popescu, Smolin, and Wouters. So I want to think about entanglement in a slightly different way. In this talk, I want to focus on the idea that it's conserved, in particular that it's conserved under local unitaries. And in physics, we're familiar with conserved quantities, things like charge, isospin, angular momentum, energy are often conserved. And when you have a conservation law, what this means in terms of the states is that the states split up into subspaces according to your conserved quantities. And your operators, either measurements or unitary operators, are constrained to respect this partition. So for example, this top thing might be angular momentum 0, this might be angular momentum 1/2, the next one might be angular momentum 1. And if you have an operator that preserves angular momentum, that carries no angular momentum of its own, then it will respect this, it'll be block diagonal accordingly. If you can even generalize this a little bit, if the operator carries some angular momentum, let's say the operator has angular momentum 1, then that means it can change the angular momentum of the state by 1. They can take 4 up to 5 or down to 3, but no further. And then it would still be sort of nearly block diagonal. So what about entanglement? How can we apply these principles to entanglement? Is there sorry, these are called super selection. Sometimes these are called selection or super selection rules. These rules saying that certain entries, in fact, most of the entries have to be 0 if they couple one charge to a different charge, then often the symmetry of the problem just forces them to be 0. So what are the analogs for entanglement? So let me rewrite the Schmidt decomposition in a slightly different way. So let me write psi as a superposition over a variable number of EPR pairs. So Alice and Bob each will have a label K that tells them how many EPR pairs they have. Then they share K EPR pairs. That's what phi2 means. It means an EPR pair. And then they're going to have n minus k zero states really just to pad things out. And I'm gonna stop writing these zeros because it makes it kind of cumbersome. Just imagine when I write out the state that they have a well-defined number of qubits, and I'm only going to write down some number of EPR pairs. And in general, there can be a different amount of weight to these different values k of number of EPR pairs, and it'll be given by some probability distribution p. So what does it mean that entanglement is a conserved quantity under local unitary operations? When we do a local unitary operation, k EPR pairs can only be mapped to k EPR pairs. And so, maybe in some different basis, but it's not going to change the amount of entanglement. So this vector p sub k should be approximately preserved by local unitaries. Now, I have to say approximate here because, of course, 100 EPR pairs and 101 EPR pairs are not orthogonal. Back in the physical picture of conserved quantities, if I have a state with electric charge 132 and another with electric charge 133, these are exactly orthogonal. They have zero overlap, no matter how close the electric charges are. But here, with EPR pairs, it's only approximately true. You have, substantial overlap between states of similar amounts of entanglement. Still, though, the overlap decays exponentially as the difference in the amount of entanglement increases, and so still this may be a useful principle. And there's one little caveat, which is what I've written is not fully general. Not everything can be written as a superposition of EPR pairs. However, if I just modify this slightly, if I take this to be the entangled state of Schmidt rank 2 to the epsilon k, then these sorts of approximations can give an epsilon approximation for any state up to LU equivalents. So intuitively this picture is pretty reasonable, but maybe this one is a little bit more precise. Okay, so what does this mean in terms of allowed operations? In what sense is the entanglement actually conserved? What this means is that if we have a transformation that uses local unitaries and q qubits of communication, if this were an exact conservation law, then that would mean if you went q into the off diagonal, after q steps off the diagonal, you would drop exactly to 0. Instead, we get kind of a soft conservation law. With q qubits of communication, you can increase the amount of entanglement by q. And so up to that much, the matrix elements could be 1. And then beyond that, they don't drop immediately to 0, but they go down exponentially as you go further from the diagonal. So the matrix, instead of looking like this, exactly block diagonal form, it looks sort of approximately block diagonal. So that's the first thing we would expect in this approximate conservation picture. The other thing we'd expect is, we're used to saying that entanglement is a resource, and maximally entangled states certainly sound like the most useful thing there. But this points to a different type of state. Here, as I'm trying to succinctly write a product state superposed with a large maximally entangled state. States like this are unusual and they seem hard to create. And they may have uses that go beyond the uses of maximally entangled states. Okay, so so this is sort of the intuition. Let's talk about this a little bit more concretely.
Sorry, Aram, can you
yes.
a little more about in what sense are you saying valuable and for those states?
Good. So we're going to see in a minute how they are hard to create from EPR pairs. And in other words, they require a lot of communication to create from EPR pairs. So in this original paradigm where the LOCC means we're allowing free classical communication. I guess I should have said this, but if the classical communication is not free, if this is something that we have to measure, then it may be difficult to create these states. And whenever something's difficult to create, it's potentially more useful. So if I have, if it's hard to make the state from EPR pairs, then there's at least one task they can do that EPR pairs can't, which is create a state like this, right? And then, once you can do one weird contrived task better than EPR pairs, and you require a lot of communication to create it, maybe there are other tasks where they can save on communication as well that are, more interesting or, that don't look like this, where they can also save on communication relative to EPR pairs. Does that make sense?
Yeah.
Good. Okay, so the first thing I want to consider is what is the communication cost to convert one state to another one. So we saw that there are constraints on LOCC to convert one state to another one, but those don't measure how much communication is required. And when you write it in this picture of superpositions of different maximally entangled states, you can rephrase this as you have one superposition over maximally entangled states with distribution P, and another superposition with distribution Q, and you'd like to map one of these to another one. And so the way you can do this is you can plot the histograms of P and Q. I mean, I guess not really histograms, just you're plotting P and Q as a function of K. So these are the distributions over how much entanglement. And so let's say P has, a peak here and here and here, and Q has a peak here and is spread out over this area. Then the cost is going to be, what I claim, the cost is going to be roughly the L infinity Earth mover distance. Okay, so what does that mean? The Earth mover distance, maybe I won't define what it is in general, but the L infinity Earth mover distance is basically saying, find a coupling between these two distributions. In other words, for every piece of mass of this distribution in P, move it to some point in Q, such that you've piled up all the dirt. Now, dirt was piled according to P, move it so the dirt is piled according to Q. And the cost of this transformation, you might ask, what is the average distance that dirt moves? That would be the L1 Earth mover distance. You might ask, what is the square root of the average square distance? That would be the L2 Earth mover distance. What we care about is the L infinity Earth mover distance, which is just what is the furthest any piece of dirt gets moved. So, if we all want, local tomatoes, what's the furthest that a tomato has to move? So in this picture, what is the length of the longest arrow? Now, this is if you want to do it exactly. If you want to do it to epsilon error, the picture is basically the same, except you're allowed to throw away or create epsilon mass wherever you like it. So it's basically the same kind of L infinity picture, but with this, epsilon fuzz factor. And so when you think about this particular state here, this has a peak at 0 entanglement and a peak at n entanglement. And so these two are very highly separated. This is going to have a high cost when you start from any maximally entangled state. When you look at this picture here, maximally entangled states just have a peak at one point. And so if you want to move it to two things that are distance n apart, you're going to need communication cost n over 2. So that's why these spread out states are always going to cost n over 2, a cost that will have a large communication cost to repair. So the lower bound, I'm going to give you a slightly stronger argument for the lower bound in a minute. The upper bound, I hope you can kind of intuitively see why it's true, which is that for every part of the superposition, you can do this mapping with the appropriate amount of communication. So once you have this kind of mapping, what you're doing is in one branch of the wave function, you're moving 100 qubits to 100 EPR pairs to 110 EPR pairs. So that takes communication cost 10. In another part, you're throwing away entanglements. You're going, let's say, from 60 down to 50. And again, that costs 10 communication. And it's a little bit tricky because in some branches, you need to use more communication than other branches, but you can get it to work out so that you just take the maximum of any of them. In some branches, you use communication without creating or destroying any entanglement. In other branches, you create a lot. In other branches, you destroy a lot. But as long as the total amount of communication you use corresponds to the Earth mover distance, then things will be okay.
I have a question.
Yes.
To destroy entanglement, why do you need communication? Can't you just like measure the EPR pairs and just like remove 10 EBITs that way?
Great. So yeah, that's an important caveat to what I'm saying. So what I'm talking about is the cost of doing this in a unitary way. Now, I couldn't hear. Was that Henry who asked the question?
Yeah.
Yeah. So right, as Henry's question was, if I want to go from 100 EPR pairs to 50 EPR pairs, there's no communication cost. I can just throw away 50 EPR pairs. In general, if I have, if Alice and Bob have two states, they have a state on A1, B1 and another state on A2, B2, they can just throw away the state on A2, B2 at no cost. And so when I say this is a communication cost, what I mean is if you don't want to throw anything away, basically. If you do want to throw something away, the thing you throw away had better be disentangled with what you keep. Otherwise, you're going to incur a lot of noise. And so there's some limited examples where you can throw things away. And in those cases, basically, P has to be written as a convolution of two distributions, right? So if you combine two states, then what happens to the distribution P is they get combined via convolution. And so if you can, there's some cases when you can just throw away a subsystem and still get an approximately pure state. But then apart from that, then the unitary part of the transformation has to look like this. Thanks. Okay, so this is the upper bound, showing that it's possible. For the lower bound, let me give you just sort of I'll give you an incomplete argument for the lower bound. But I think that one that gives you a sense of why it should be true, hopefully, which is, suppose this is my state. So I've put in Schmidt normal form, and I've sorted the Schmidt values. And I'd like to start from many EPR pairs and map to this state. Then when you put it into this language, the Earth mover distance is given by the log of the top Schmidt value, lambda1, times the Schmidt rank, R, divided by 2. And so I'll call this the entanglement spread of psi. In this picture of where you have a superposition of EPR pairs, this is the approximate width of that distribution. And the reason why this is a lower bound is every time if you start from a bunch of EPR pairs, then this quantity is initially 0, because if you have many, many EPR pairs, the top Schmidt value is just 1 over R. So delta is initially 0. And then every time you transmit a qubit, the Schmidt rank can go up by at most a factor of 2, and lambda1 can go down or up by at most a factor of 2. And so this delta starts at 1, it increases by at most 1 per qubit sent, and so it's just simply a conserved quantity. And you can do approximate versions of this as well that give you, that behave more or less how you'd expect. And if you want to use this picture where you have a superposition of different number of EPR pairs with a distribution P, then the spread here is the width of the support of this distribution. So going back to this example, if you have a pure state superposed with a maximally entangled state, then the R is roughly 2 to the n. Lambda1 is about a half. And so creating this product is about 2 to the n. So creating it requires nearly n over 2 qubits of communication. Which roughly matches the bound if you just start from n over 2 EPR pairs, and in one branch of the wave function, you boost this up to n, and the other branch, you unitarily drop it down to 0 EPR pairs. So we have a lower bound that roughly matches the upper bound. And the general lower bound uses similar ideas, but it's, yeah, this is in my paper with Matt Hudron. I won't present it now, but hopefully this gives you the idea of why such a thing is plausible. So entanglement, okay, so what have we done so far? We've said that entanglement spread characterizes the cost of preparing a state. It's an upper and lower bound on the cost of preparing the state from EPR pairs. Now I claim it's also an upper and lower bound on the cost of checking whether you have a state. So suppose I'd like to do this 2-outcome measurement. I want to see, do I have a state psi or identity minus, or or not, right? The orthogonal complement. The unitary version of this is I want to perform a reflection about the state psi. And these are, in general, these are roughly equivalent tasks. And I claim the communication cost is going to scale with the spread of psi, plus there's a small, because the protocols we have for this are approximate, there might be a small dependence on the error, but it goes like log 1 over epsilon, independent of the total dimension or even any other features of the state. And along the lines of entanglement spread being the valuable resource, free EPR pairs do not change this at all. They don't improve the communication cost of this task at all. But other states can. Other states can, bring it down to order log 1 over epsilon if you have a general, if you're allowed the assistance of other states other than EPR pairs. So entanglement spread, in other words, characterizes both the cost to prepare a state from EPR pairs, but also the cost to test it. Any questions so far? Okay, so let me give you the idea of the lower bound here. And again, for the lower bound, I'll illustrate it just for this particular state. But the idea is pretty similar for a general state. So suppose I could test whether I have n01 tensor n plus phi2 tensor n, or the entire orthogonal subspace. One easier task is to say, well, suppose I'm given the state with either the plus or the minus superposition. And yeah, so Anurag is asking about the expander-based test for EPR states. And for those of you who don't know what he's talking about, we're going to, I'll come back to this in a minute, basically. But for now, the answer is it's going to use this result as a subroutine. You could say, or a generalized. Okay, so suppose my task is the easier one. I just want to distinguish these two states. So I'm given a superposition of 0, 1 plus n EPR pairs, with product state plus n EPR pairs or product state minus n EPR pairs. How can I tell those apart? Now, if I use a lot of communication, Bob could just send over all of his qubits and then Alice can make the test, right? But how can they do this with a small amount of communication? And if you look at this task of distinguishing the two, distinguishing them is roughly equivalent to putting a phase on one of them. So imagine doing a sigma z gate in this basis, right? Phase of 1 from one of the states minus 1 for the other state. Doing that is equivalent to doing a sigma x in the conjugate basis. And what is the conjugate basis? It's the product state and the maximally entangled state. So being able to do a phase here is completely equivalent to being able to unitarily swap these two. So to take a product state and map it to a maximally entangled state, and take a maximally entangled state and map it to a product state. And what's interesting about this is that if you're going to do it unitarily, it's hard to do even with EPR assistance. So if I have 1 million EPR pairs and I want to map it to 1 million plus 100 EPR pairs, I still need 100 qubits of communication. The fact that I have 1 million EPR pairs sitting around doesn't help me. And here it's crucial that the method of doing it is unitary. So if I'm going to use some sort of entanglement assistance, that I need to be able to return it in an intact form. On the other hand, why can other states help? Well, first of all, there's a state called an embezzling state due to Van Dam and Hayden. And an embezzling state is remarkable in that if you have an entanglement embezzling state and local unitaries, you can use that to approximately create any entangled state. So it's sort of a universal communication-free state creator. And then one particular state that would be very helpful if I want to do this task is to have many copies of psi. In particular, suppose I have k minus 1 copies of psi, and then I would have one additional state, and I want to know, is this psi or orthogonal to it? If it's psi, then altogether I have k copies of psi. If it's orthogonal, then I have k copies of psi, and then some other state, which I'll call psi perp. And it turns out these two cases can be distinguished without knowing what psi is using order log k qubits of communication. And the reason is this state lives in the symmetric subspace, and so it's invariant under cyclic permutation. And this thing changes a lot under cyclic permutation. And it only takes log k qubits to specify a cyclic permutation of k objects. So EPR assistance is really very different than other kinds of assistance. Okay, so that is the lower bound. What about the upper bound? For the upper bound, let me specialize to the case of EPR testing. So suppose that Alice and Bob share the state psi, and they want to know.
Aram, can I ask
Yeah.
a question on the previous slide? So, so the state that you, the helper state was a function of the state that you were trying to distinguish here. What if what if you asked instead of EPR pairs, if you had a helper state, but it was independent of the state
Right.
you're trying to test? Can it help at all?
Yes, that's an embezzling state.
Okay. All right.
Yeah.
I
No
see.
problem. By the way, if you want a good open problem, suppose you have a subspace. You want to distinguish a subspace pi. You want to measure pi versus identity minus pi. And you're allowed a helper state. Now, and let's say that the rank of the projector is R. Now we know that if pi is the symmetric subspace, then this is the swap operator. And of course, the communication cost of that is going to go like log R. So log R is a lower bound. But by repeating this protocol with R different helper states, the best upper bound I can get is order R. So, I believe there's a helper state that should be able to get it down to log R, but I haven't been able to find one. Okay, so let me talk about the upper bound. If psi is a maximally entangled state, the spread is 0. So this says you should be able to test if you have a maximally entangled state with an amount of communication that is independent of the size of the state. This just depends on the precision. So let's work out how that goes. Let's suppose the state is an n-dimensional maximally entangled state. Alice and Bob share psi, and they want to know if they indeed have the maximally entangled state. So one thing they can do is they say, well, look, if it's maximally entangled, it should be invariant under U tensor U star. So if they have a little control register, let's say of dimension t, then Alice can use that to do a controlled UI, and Bob can use it to do a controlled UI star. The true maximally entangled state is going to be invariant under all of those. So the control register will stay exactly the same. And so if Alice starts with the control register, she applies U sub I, then she sends it over to Bob using log t qubits, then Bob applies UI star and then checks whether the control register is unchanged. If they share a maximally entangled state, then yes, the control register will be unchanged. However, if it's not a maximally entangled state, maybe these U's will take it all over the place, each one to something nearly orthogonal. This will become very entangled. These two registers will become very entangled, and Bob's measurement will probably yield that it's not in the original state. That is the intuition. So C is the unique state invariant under U tensor U star. And indeed, this is the case if they want error lambda, they need to transmit order log 1 over lambda qubits. And I think I want to just not go into too much of the details here. Basically, the sub-normalized output state given acceptance is this one, which is 1 over t sum over ui tensor ui star applied to psi, and the acceptance probability is this bra psi m dagger m psi. And so the key claim to the validity of the protocol is that this m operator, this thing right here, is a good approximate the projector onto the maximally entangled state up to some precision lambda. Okay, so the error of the protocol will depend on what this lambda is. And it turns out that this is basically equivalent to being a quantum expander. So we say that a collection of unitaries is a quantum expander if for any traceless operator x, averaging over these unitaries shrinks x in Frobenius norm. It shrinks it by a factor of lambda. And that's analogous to a classical T-regular expander graph, which you can view as a collection of permutations, that if you apply them to any vector that adds up to 0, it'll shrink the 2 norm of that vector by a factor of lambda. And here we know that random unitaries are good expanders, just like random graphs. Random unitaries are good quantum expanders, just like random graphs are good classical expanders. And the crucial thing about expanders is that the expansion coefficient just depends on the degree. It does not depend on the size of the graph. And same thing is true for quantum expanders. This lambda parameter depends on the number of unitaries, does not depend on the dimension n. So what this means is that the communication you need is log 1 over epsilon. And so to return to this theorem, we have an order log 1 over epsilon upper bound to do this for the special case of testing if you have a particular maximally entangled state. But then this can extend to any other state, because we know if you have any other state, you can map it to some maximally entangled state using an amount of communication given by the entanglement spread of that state. So for any state, psi, you can map it to maximally entangled, test whether you're maximally entangled, and then map back. And the communication cost of that is going to go like the entanglement spread of the state plus this order log 1 over epsilon. And so this is the upper bound that matches our lower bound for doing this this state testing. So now we've seen that entanglement spread characterizes the cost to repair a state as well as the cost to test whether you have it. Okay, so this is really, I would say, just like the basics of entanglement spread. So, these are kind of like very, low-level subroutines, right? So what is sort of an operational task that is interesting that we want to use this for? And I'm probably going a little too slowly, so I probably don't have time to. I should probably skip a few topics. So let me skip. One thing we used this for a long time ago was the quantum reverse Shannon theorem. I'm going to skip all that. Let me talk about area laws and communication complexity. So one topic where everyone who hangs out at Berkeley and does quantum information knows about all the exciting progress in the local Hamiltonian problem that's come out here. And one of the central, one big insight is that if your Hamiltonian is local, then the ground state should, and it's gapped, there's a gap between the bottom 2 eigenvalues, the ground state should inherit the locality. And there are many versions of this. So if the ground state is gapped, then if the Hamiltonian is gapped, then the ground state should have correlation decay, and also should have an area law, and also should have an MPS description. And all of those are sort of different ways of saying that it keeps the locality. And what the area law conjecture says is that the entanglement of a subregion should scale like the size of the perimeter of that region. And more precisely, if you have a bunch of edges going from inside the region to outside, then you should add up the dimensions of all the particles along the edges, and that should be a measure of the basically of the perimeter of that region. And so one thing that came out of this Simon's reunion workshop that I went to previously was this paper where we found a counterexample to that area law conjecture, that we found a very simple system with 4 particles, 2 of them of dimension n, and then 2 qubits in the middle. And if you put this box around the left 2 particles, then you find that the gap is order 1, the boundary is order 1, and yet the entanglement is near maximalist, log n. And if you want to do it just with qubits, there's kind of a qubit version as well. And so what this suggests is that, maybe the area law conjecture, you need to really think more about the perimeter, like about the boundary, because maybe the amount of entanglement shouldn't depend just on the number of edges that you cut, but because we have this exponentially decaying correlations, we should allow contribution of entanglement from things near the boundary as well. So a revised area law conjecture would be that the entanglement is, if you have this red cut, then you get full contributions from stuff right next to the cut, then like a little bit lower contribution from stuff further away. And as you get further away, you get exponentially decaying contributions. So that is a reasonable conjecture. And you could say, like, the exact area law conjecture that the entanglement just comes from the edges that you cut, that was unreasonable. That was like too much to ask. So us falsifying it, we were falsifying an unreasonable version of the conjecture. However, this exact area law, where you get a contribution to the entanglement just from the bonds that are cut, turns out to be true for entanglement spread. So it turns out to be true that the entanglement spread of the ground state is upper bounded by really the exact edges that are cut divided by the gap. And actually, another result, which I won't have time to present, is if you allow this fuzzy version where you spread out if you look at nearby edges, then the spread is actually bounded by the square root of that. And I should mention that an exact area law was also known for the thermal area law. So if you look at thermal states and you look not at their entropy, because that's large, but their mutual information, it turns out that obeys a similar bound. So so what is the proof here? It really follows quickly from the statements I gave before. So first, we argue that Alice and Bob can estimate the energy of a state to error epsilon. Sorry, this should be delta A over epsilon, not delta A over gap. Sorry, using delta A over epsilon quantum communication. And the proof is to use phase estimation, right? So if you want to estimate the energy of something, you should do e to the minus IHT for some superposition of different t's. And if you write t as HA plus HB plus a boundary term, then you really want them to only pay the communication cost of the boundary term. And this is achieved by this beautiful Hamiltonian simulation paper of Guanghao Lo and Nathan Levy. And the communication cost that results just scales like the size of the perimeter divided by epsilon. And so what this means is that if you want to implement a reflection about the ground state with error given by the spectral gap, then the cost goes like the perimeter divided by the gap. And we know, on the other hand, that to implement this reflection, the cost should be at least the entanglement spread of the ground state. And so this proves that the entanglement spread cannot be that large. So these exotic states, like superposition of product state and maximally entangled states, can't arise as ground states of local Hamiltonians. Okay, and so the last thing I want to talk about, I think I have like 2 or 3 minutes left, right? I said these are potentially valuable in communication complexity. So by this, I mean, Alice and Bob get some string, they want to compute some joint function, and they're allowed to, either communicate one way or two way. We know that shared randomness can only help a limited amount. if you have a giant strings, you can de-randomize them by something called Newman's theorem and just use a subset of those strings. Entanglement does seem to help, but the only way we've used it to help is with teleportation. In other words, taking classical communication and turning it into quantum. We don't know if vastly larger amounts of EPR pairs would help. And you might wonder whether other kinds of entangled states, like embezzling states, can save even more communication. But Matt Kudran and I showed that general entanglement cannot really help. And the argument is quite simple. Suppose you have, this is your starting state. This is the most general possible thing, right? Where you have superposition of different numbers of EPR pairs, and your protocol only uses Q qubits of communication. Then the acceptance probability will depend on your state as follows. The amplitudes of your state will be sandwiched by your protocol, and your protocol has these decaying off diagonal terms. So once you get far off the diagonal, these things are going to be mostly zero. And so it's not going to be sensitive to superpositions between very different amounts of entanglement. So if you were to feed in, for example, the state of product state plus a gazillion EPR pairs, you could have used product state minus a gazillion EPR pairs, and the protocol wouldn't be able to tell the difference. So then you also could have used a mixture. And so that can be done just with EPR pairs. And so you never need to have a superposition of large amounts of entanglement. You never need to have a lot of spread. The most spread you need is going to go like, I guess they were poly, that should have been big O of Q over epsilon. And so large amounts of entanglement spread don't help. Now for this, now what this relies on is that you can at least communicate between Alice and Bob. If you're in the simultaneous message passing model or like a Bell testing model, then entanglement spread does help. So, there's one paper due to Regev that does this, and another, I think due to Toner and Vayner that show this for like the Bell testing scenario. Okay, so for these two applications, the big question is, does entanglement help in communication complexity? For area law, we want to know, do ground states satisfy an area law? And what I can argue using this analysis of entanglement spread is that for communication complexity, do very large entangled states help? Well, you can at least reduce the problem to EPR pair. And then for the area law question, we'd like to know, do entangled states have a ton of entanglement? Well, we can at least assume this entanglement is of an EPR-like form. And so I hope that this represents progress on these questions. Whether they'll lead to their ultimate resolution remains to be seen, but they arguably move it into a simpler form where instead of considering arbitrary states, we can just consider nearly maximally entangled ones. And as I've mentioned, this work has been an on and off part of my career since the beginning. I began with this root end lower bound for entanglement dilution. Then with Debbie Lung, did a state testing lower bound, a review paper of it, and then used it for the quantum reverse Shannon theorem. Then did this paper at the reunion workshop where we did the cheap EPR testing and the counterexample to the area law. With Matt Kudran, we showed the Earth mover distance bound and showed that it doesn't help with communication complexity. And then finally with Anurag Anshu and Mehdi Solmanfar, we gave this entanglement spread area law. So it's been fun to work at it. I want to thank all of my co-authors for the many years of fun and productive collaborations. Thanks to Simon Institute for hosting me. It's been super fun each time. And thank you, Umesh, for inviting me this time. Okay, and thanks to you for your attention. I'll stop now.
Thanks, Aram. I think we have time for maybe one short question, if there are any.
Was there a more precise statement about, the area law being able to restrict to EPR-like states?
The more precise. Okay, so the statement is the ground state has an entanglement spread. The point is if the entanglement spread is low, then the ground state is EPR-like.
Okay.
Right.
Yeah.
So we give two upper bounds. Our paper gives two upper bounds on the entanglement spread of the ground state. The first one is based on the one I presented, where it's exactly the number of edges that are cut divided by the gap. And the second one says, if you're willing to consider edges within an order 1 neighborhood of the cut, then you actually can get square root of that, square root of the number of edges. But both of them are upper bounds on the approximate entanglement spread of the ground state.
Great. Thanks. That was a great talk.
Thank you.
Let's thank Aram again. So next up,